Welcome to the next episode of Advanced Quantum Mechanics. I'm your host, Ref Bari, Brown University physics graduate student, and today I'm going to give you a full, detailed explanation of second quantization, which is one of the most fundamental things in quantum field theory. In second quantization, waves behave like particles. Now, that might seem very hand-wavy. What does that even mean? In today's lecture, I'll show you exactly what that means. If you have n coupled oscillators, imagine not only one spring, but n springs connected to each other, then those n springs, even though they're connected in position space, you can transform via the Fourier transform into momentum space and decouple the n oscillators into individual oscillators. And these individual oscillators behave much like particles, each with an energy h bar omega. So these individual particles are called phonons, and they're very similar to photons in an electromagnetic field. So these quantized oscillator particles are phonons, and you can decouple our n coupled oscillators by Fourier transforming to momentum space. So the moral of today's story, the moral of the story is going to be that waves behave like particles. And you can see that a wave like Hamiltonian, like the simple harmonic oscillator, gives rise to particle-like solutions in terms of phonons. But the only way you can see those particle-like solutions is if you Fourier transform to momentum space. In Fourier, in position space, those solutions are, you cannot get the solution, right? The solution is entangled, the Hamiltonian is coupled. But if you Fourier transform, you see those particle-like solutions emerge straight out of the Hamiltonian. Let's go ahead and check out the physics. All right, folks, so first let's start off with the simple harmonic oscillator in quantum mechanics. Now, of course, we've all seen the solution to the simple harmonic oscillator, but it never hurts to go through it one more time because it keeps appearing over and over again in quantum field theory. So let's go ahead and check that out. First thing I'm going to do is write down the Hamiltonian for a simple harmonic oscillator. So, of course, a simple harmonic oscillator for the uninitiated is simply basically a box attached to a spring. And its Hamiltonian is as follows. We have the kinetic energy, p squared over 2m, and the potential energy, 1/2 m omega squared x squared, right? That's all there is to it. You can see just how disgraceful it is, okay? M omega over pi h bar to the 1/4, your Hermite polynomials, times e to the minus epsilon squared over 2, where this epsilon is equal to the square root of m omega over h bar times x. So you don't need to know any of this, okay? All of this is completely useless, except for this right here, this exponential. This exponential, this Gaussian, in fact, tells you that the solutions to the simple harmonic oscillator look something like this. If I were to plot these solutions, then like this, exactly like a Gaussian, as you might expect. Okay, it's e to the minus x squared over 2. The second eigenstate of this simple harmonic oscillator, psi 1 of x, looks something like this. Okay, once again, you have something that looks like a Gaussian. Okay, and so on and so forth. The third one, let me draw the third one over the first one. Okay, the third one looks something like this, right? So this is psi 2 of x, and so on and so forth. So that's how the solutions for the simple harmonic oscillator look like. Now, that's how the eigenstates look like. What about the eigenenergies? Well, famously, the eigenenergies for the simple harmonic oscillator are discretely spaced, right? So the ground state energy for the simple harmonic oscillator, as you might know, is 1/2 h bar omega, and thereafter, the energy levels are spaced by h bar omega. So the second energy level, for example, is 3/2 h bar omega. The third is 5/2 h bar omega, and so on and so forth as we proceed upwards. Okay? So for example, if you have some kind of a particle on the ground state energy level, then it would need to receive exactly h bar omega of energy to jump up to the second energy level, 3/2 h bar omega. Okay? And so the famous way we do that is by using ladder operators. Ladder operators are tools, technological tools to help us jump from the ground state energy to the first energy, from the first energy to the second energy level, and so on and so forth. So the ladder operators are these tools to help us jump from one energy level to another. So we have two ladder operators, a dagger, the creation operator, which helps us increase energy levels, put quanta of energy into the simple harmonic oscillator, and we have the opposite. We have the annihilation operator, just A. This A helps us lower energy levels, okay? So this is called the annihilation operator because it destroys quantum packets of energy from the simple harmonic oscillator, okay? So my goal right now is to show you how to derive A dagger and A. So let's go ahead and do that. So I'm going to pull up a new board, and it's actually fairly trivial, not trivial, but it is very straightforward to derive these ladder operators, and it never hurts to see where they come from. So let's go ahead and do it. My first order of business is to write down the Hamiltonian once again. So p squared over 2m plus 1/2 m omega squared x squared, where omega is square root of k over m, and so k is m omega squared. So this is simply the spring potential energy, 1/2 kx squared. I replaced k with m omega squared as usual. So now what I'm going to do is we're going to do some gymnastics here, some mathematical gymnastics. I'm going to factor out 1/2 m omega squared from this. So if I do that, I get x squared. By the way, this should be an operator. I get x squared, and then here, what do I get from momenta? Let's see. I certainly get p squared. I've already got the 2 out. Now, here I have an over m, but this is just multiplying by m. So I need to divide it by m squared, and I also need divided by omega squared. Let's see if this reproduces our original Hamiltonian. So I have 1/2 m omega squared x squared plus 1/2 m omega squared p squared over m omega squared m squared. So m cancels with m squared, omega squared cancels. I get p squared over 2m as desired, and 1/2 m omega squared x squared as desired. So okay, so this is so far so good. Now, looking at this, you might think, wait a second, maybe there's a way I can factor this out. This looks like a difference of perfect squares if I use complex numbers. So here's what I mean. Maybe I could factor this out as 1/2 m omega squared of x plus I p hat, this is also an operator, m omega, times x minus I p hat over m omega. Now, if you were to do this with regular operators, operators that commute with each other, this would be perfectly valid. But we know that the position and momenta operators do not commute with each other, right? They're IH bar times delta IJ, right? This is the fundamental canonical commutation relation, and it tells us that x and p don't commute. That means this is not actually equal to this. It's close, but not quite. How close? Well, let's FOIL it out and see. This is equal to 1/2 m omega squared. Now let's FOIL this thing out. So I'm going to have x times x, which is simply x squared. Now x times p, let's see what that is. So I'm going to have x p here plus I over m omega. Here I'm going to have p times x, which is not the same as x times p. If they commuted and they were the same, these two would cancel out. I'd reproduce my original Hamiltonian. But they're not the same. They don't commute. So that is a problem. Not really a problem. It's something we'll have to fix. And finally, I have, let's see, I have I times I is minus 1. Minus 1 times 1 gives me plus p squared over 2m. And let me end this bracket here. So I have this for my Hamiltonian. This is not quite my original Hamiltonian because of these two terms. So how are we going to deal with these two terms? Well, let's check them out. So I have m omega squared, okay? So I have the two terms that I do want, right? X squared plus p squared over, let's see, this should not be 2m, should it? This should be p squared over m squared. So that's m squared. And yeah, I obviously did not know what I was writing. This is p squared over m p squared over m squared omega squared, right? M squared omega squared p squared. Very good. Okay, so this is m squared omega squared. So this is this, but with this extra factor of I over m omega times px. Let's see, maybe I should use a minus sign. Let's use a minus sign here so that I can write xp minus px. The reason I wanted to do that is so that I could write it in the exact same way as the canonical commutation relation. So what is xp minus px if not the commutation between x and p, which we know, if they're in the same direction, to be I h bar. So I can rewrite this whole thing. Okay, let me go ahead and write everything out. Maybe I should go to the next board. Oh, the next board is also full. So let's go to the next board. Let's pull this one down. Okay. So let's take this out. Seems like we had a math class here, a rather trivial one at that. So going back to our what we just wrote down, we have 1/2 m omega squared x hat squared. That's my first term here. Let's distribute out, produce the second term, p squared over 2m. Now let's produce our third term over here, which is going to be, let's see, so I have minus I over m omega. I've got 1/2 m omega squared, and I've got the commutation relation, which gives me I h bar. So let's see what I've got here. So first of all, m and m cancel. I've got I times I is -1, makes this a positive. And so I'm left with 1/2 h bar omega squared. Now, looks like I might have made a small silly mistake. Let me double check my work here. So this is, I should simply get h bar omega over 2. I'm not sure. Oh, silly me. Omega goes into omega squared once. So all of this to say that the Hamiltonian, not my original Hamiltonian, but whatever this factorization produces is something very close to my original Hamiltonian, but not quite. It's 1/2 m omega squared x squared plus p squared over 2m plus h bar omega over 2. So all of this to say that this Hamiltonian is just a little bit off from my original. Okay, so if I go back to what I just wrote down over here. Okay, so this factorization is off from my original Hamiltonian, but if I just subtract this factor of h bar over 2, then I reproduce my original Hamiltonian. So that's exactly what I'm going to do. Subtract this factor of h bar over 2. Depending on the order in which you place these two factors, you might have to do a plus instead of subtract, but that doesn't really matter. It's just a constant that you're adding or subtracting anyway. What matters is that this is a correction factor that will eventually turn out to be the ground state energy of the simple harmonic oscillator. So in any case, this right here, x plus ip, I'm going to call that, let me make sure that I don't mess up which one I call a and which one I call a dagger. So x plus ip over m omega, I'll call this my annihilation operator. And this right here, x minus ip over m omega, I'll call this my creation operator, up to a constant factor, which we'll trivially determine. So my annihilation operator is given by x plus ip over m omega, and my annihilation operator, my creation operator is x, what am I writing? X minus ip over m omega. Okay, and these are both defined up to a constant. Okay, so these are both defined up to a constant k, which we will be able to determine. And so that is the creation and annihilation operator. So this is the annihilation operator, annihilation, and this is the creation operator. Okay, so very good. And one very important fact to remember is that the complex conjugate or dagger of A of the creation operator is the annihilation operator, and vice versa. and the commutation relation between A and A dagger is 1. Okay, so these are important facts to remember. And one final thing to mention, okay, is the action of A and A dagger on states. So if I act with the creation operator on a state n, then I will produce the square root of n plus 1, ket n plus 1. So I've essentially jumped up a state in the simple harmonic oscillator. So if I go back to this picture, that means I've jumped from ket n to ket n plus 1. That's what the creation operator enables me to do. And similarly, the annihilation operator takes me down a state. So when the annihilation operator acts on ket n, it gives me ket n minus 1 times some normalization factor. So these two facts are also incredibly important. Okay, so that is the main idea behind creation and annihilation operators. I believe that is pretty much it for this part of the lecture. And now let's take a look at n coupled oscillators. So not only one oscillator, but n oscillators connected together. Let's take a look. Welcome to the last part of today's lecture, God willing. In this part, I'm going to demonstrate that if you have a chain of linear coupled oscillators, there's a way that you can unentangle the oscillators by transforming from position space to momentum space. Let's demonstrate that. First, I'm going to draw a picture of coupled oscillators. So here's the picture we're considering. So we have a bunch of masses which are all connected. This is our linear chain of oscillators, and each one of these masses have the same mass, let's say m, and this is the j minus 1th mass, this is the jth mass, this is the j plus 1th mass. And what we're going to say is that each one of these masses can be displaced by some amount. So let's say that this is the equilibrium position, and this is the new position of the mass after it's been displaced. And each mass can be displaced by, let's say, an amount x sub j, okay? And the normal position of the mass, okay, from some origin is given by j times a, okay? So what is a? A is the spacing between each of these masses. So a is the distance between the j minus 1 and jth mass, and therefore the location of the jth mass is going to be j times a, simply the lattice spacing times the number of springs that were before it. Okay, so hopefully I've encoded all the information here. So this is r sub j. The position of the jth spring is simply j times a. Okay, now first thing I'm going to do is write down the Hamiltonian for this system, as we do with any physical system, right? Write down the Hamiltonian. So let's write it down over here. Let me use yellow. So the Hamiltonian for our system is simply going to be the momentum or kinetic energy, so p squared over 2m, the momentum associated with the jth mass, plus 1/2, and we're going to have our spring energy, 1/2 kx squared, where x is xj plus 1 minus xj, right? So xj plus 1 minus xj gives you the distance between each spring, and thereby gives you how much each spring has been displaced. So this is our Hamiltonian here for this physical system. Pretty straightforward. Now the next thing I'm going to do is let's take a look at the position and momentum of each one of these masses. Okay, so here's what I'm going to do. Here's the big picture. I'm going to take a look at the position and momenta of each of these masses, and I'm going to transform from position space to momenta space. So that's xk tilde, pk tilde. So just to clarify, this right here, we were originally in position space, okay? Position space. And then we're going to Fourier transform. This is a Fourier transform that we're going to do here to momentum space. Momentum space. Very good. So let's go ahead and do that. So the first thing I'm going to do is write down the coordinates for my masses in position space. So that's going to be x sub j is equal to, so I have just some summation. I have my plane wave as is normal for transforming using the Fourier transform, and then times x sub k. Okay, so what, wait, I should be summing over k here so that at the very end I end up with j's. So okay, so I'm summing over these frequency components, and I'm weighting each of these frequency components by this exponential plane wave factor here. And after I sum over all the k's, I should be left over with a j right at the end, as indeed I do. And I'm just going to put a normalization factor of 1 over n here, where n is the total number of springs. Now, likewise, p sub j, the momenta associated with the jth spring, can be transformed from Fourier space, from momenta space, by a Fourier transform of the following type, p sub k tilde. Okay, now the only change that I'm going to make from this statement is I'm going to replace x sub j with the value of x sub j, which is ja, right? That's the location of the jth mass. So this right here is ja. Likewise, this right here is also ja. Okay. Okay, very good. So now what we're going to do is we have all of this. I'm going to now write all of these elements in momentum space. So this was in position space. Let's take a look at all of this in momentum space after we Fourier transform this. So let's Fourier transform all of these folks. So in momentum space, I'm going to have x sub k tilde is equal to, once again, my normalization factor. That's not important, but what is important are my exponentials, which are now negative because I'm transforming back from position space into momentum space. And here I'm going to have x sub j. And likewise, I'm going to have p sub k tilde is 1 over square root of n. The summation, now my summation is now going to be over j, so that I'm just left with a function of k at the end. E to the minus I k j p sub j. So this should be correct, and indeed it looks correct. So this is our position and momenta for the jth spring in position space, and after we Fourier transform in momenta space. So now, what is the whole point of doing that? The whole point of doing that is to show you this. Take a look at our Hamiltonian right here. If you look at the potential term of our Hamiltonian, you'll notice this coupling factor that couples the j plus 1 spring with the jth spring. That makes this problem extremely difficult to solve from an analytical standpoint, right? So the question is, can we uncouple these springs somehow? Can we somehow remove their links from each other? And the answer is yes. Yes, we can. We can uncouple this oscillation term by transforming from position space to momentum space. And so that's what we're going to do right now. So I'm going to replace p sub j with p sub k tilde, and x sub j plus 1 and x sub j with x k tilde. Okay, so I'm going to do that in just a second, but first I have to prove two mathematical quick identities. Okay, so let's go ahead and do that. First thing I'm going to do is show you that by imposing periodic boundary conditions, I'm going to quantize the momentum associated with each of these springs. So by creating some periodic boundary conditions over here, okay, so periodic boundary conditions, and forcing these periodic boundary conditions forces the momenta of each of these springs to become quantized, as I will show right now. So mathematically, what that means is, where is our, right. So mathematically, that means our exponential e to the ikx sub j has to remain the same even after I move over by n springs, right? So once I move over by n springs, I had better return to the same position, right? So this is a periodic boundary condition. Now x sub j is simply ja, and so now what I'm really saying is that after I walk over by n springs, I had better end up with the same plane wave scaling factor. So what does this mean? This means that I can expand this as e to the ikj a times e to the ik n a. This is equal to e to the ikj a on the other side. That means that this factor right here, this exponential right here, had better be 1. Okay? So if this exponential factor is 1, that tells us something about its exponential, its power. So if e to the ikna is 1, that means that exponential ikna, well, I is not part of it, is some multiple of 2 pi, right? Because e to the 2 pi I is 1. So that means this is some multiple of 2 pi. That means that k, the wave vector, the wave number associated with our jth spring, is 2 pi m over n times a. Let's see if that's correct. Indeed it is. So this is the quantized momentum associated with the jth spring, right? So you can see the quantized momentum occurs as a result of these periodic boundary conditions that we placed on either end of our system. Okay, now I'm going to prove a mathematical identity which is going to help us as we substitute in the momenta and position in momentum space. Okay, so let's go ahead and take a look at our mathematical identity. So here's the identity I'm going to set out to prove. The summation of plane waves e to the I, maybe I should write it as e to the ik minus k prime ja. The summation of these plane waves over position space, over j, gives rise to a delta function, n delta k prime. Hopefully that's correct. Indeed it is. So this is what I'm going to set out to prove right now. This is going to make our physics calculations much easier down the road. So let's first prove this, okay? So how are we going to prove this? Well, the first thing I'm going to do is do casework. By the way, if you're wondering why I'm about to prove this, let me just show you that this is exactly what we have over here, right? In these exponential factors in our Fourier transforms, right? This right here is simply x sub j. This is simply x sub j. And this e to the I k x sub j is exactly what you observe right here as the factors for our position and momenta for the jth spring, and position and momenta for the jth spring in momentum space. So that's why we're trying to prove this identity so that we could simplify these summations. Okay, so let's take a look at how we are going to go about proving this. I'm going to just do simple casework. Okay, case 1. Imagine that k equals k prime. Well, in that case, what are we going to end up with? Well, we have the summation of e to the I. If k equals k1, if k equals k prime, then I simply have 0 here times ja summed over all j's from j equals 0 to n. So this simply gives me the summation of 1 from 0 to n, which is simply n. Okay, and what about case 2? This one is a bit more involved, but we can do it. In case 2, k is not equal to k prime, so that we have the following. The summation of e to the I, k minus k prime, ja. Now, how do you solve this? Well, you have to use sequences and series. Recall the equation for the sum of a geometric series is as follows. Actually, I don't remember, so I'm going to have to derive it from scratch. Let's derive it. So let's say you have a geometric series of the following form. Let me make sure that my form is correct. So consider a geometric series of the form a plus ar squared, so on and so forth. Okay? And let's say our final term here for this geometric series is ar n minus 1. So this geometric series has some sum, and our goal is to figure out what the sum of this geometric series is. Well, we can simply multiply our geometric series by r. So if we multiply each one of these by r, then a multiplied by r becomes ar multiplied by r becomes ar squared, and so on and so forth until ar to the n minus 1 multiplied by r becomes ar to the n. So now, if I go ahead and subtract these two terms, then I'll be left with S factored out times 1 minus R is equal to, now all of these terms cancel out, and I'm simply left with A minus A R to the N. Okay, well, so now if I simply solve for the sum of the geometric series, that's simply A 1 minus R to the N over 1 minus R. Let me just double check. That is indeed correct. So this is the sum of an arbitrary geometric series with n terms. And we're going to employ that to sum this geometric series right here. So in this geometric series, what do we have? Well, we have, what is our first term? Let's maybe, if we write out a few of the terms here, that's going to help us simplify this. So let's first write out a few of the beginning terms. So when j is 0, then I have e to the I k minus k prime 0 times a. Now that's of course 1. That's of course 1. And so that already tells us what our first term is going to be. That's our value for a. It's simply 1. Okay, and what's our geometric ratio r? Well, that's simply going to be this. It's going to be e to the I, k minus k prime j a. So now we can substitute into our summation formula for geometric series so that s is equal to a, which is simply 1. So 1 times 1 minus r to the n. So that's e to the I k minus k prime n j a divided by 1 minus r, where r is e to the I k minus k prime j a. Okay, now here's the kicker. So first thing, okay, so this is so far so good. First of all, remember our periodic boundary conditions. Okay, our periodic boundary conditions state that e to the ikj, where is it? E to the ikja is equal to e to the ikj plus n times 1. Okay, so what does that mean? That means, let's take a look at this term right here. Take a look at this term, and there should be a j here. Am I missing a j? No. Okay, so there should not be a j here. Maybe I am right. Okay, I made a mistake. You see, the common geometric ratio is not e to the I k minus k prime j times a. No, each multiplying factor is with j equals 1. Right? If you just write out the first few terms of this series, you'll observe that. Right? The first few terms of this series, let me write them down over here, are simply 1 for the first term, as we observed previously. But if j is 1, then we have our second term, e to the I k times k prime times a. And so now you can see that the common ratio is not j times a, it's simply a, right? It's e to the I k minus k prime times a. And so I should not have written j over here or j over here. Okay? So now if I observe my statement here for periodic boundary conditions, that helps me simplify this summation. Because recall that e to the I k and a is 1, right, by periodic boundary conditions. Or if I generalize this, e to the I k minus k prime and a equals 1. That means this entire term right here is equal to 1. Maybe that doesn't really look like 1. Let me write that again. This is equal to 1. So 1 minus 1 is simply 0. This is simply 0. So our summation is simply 0, meaning that we have one of either two possibilities. So if k equals k prime, then our summation equals n. And if k is not equal to k prime, then our summation equals 0. So how do we express that mathematically in a compact way? We say n delta k comma k prime. So that if k equals k prime, then we activate the delta function, and this gives us n. But if k is not equal to k prime, then the delta function collapses to 0. So our summation collapses to 0. So that is the finding of our first mathematical trick. Okay, so that is that. Now I'm going to prove a second mathematical trick, which, trust me, is going to help us loads in eventually computing the Hamiltonian for the system in momentum space. Okay, in position space, these guys are coupled, These springs are coupled together. That's the problem. But when we Fourier transform into momentum space, they're going to become uncoupled springs, okay? But to demonstrate that, I first need to show you yet another mathematical trick. So let's cut to that. All right, so as part of transforming from position space to momentum space, we're going to be forced to evaluate summations that look like this. Let me just motivate where this comes from before I evaluate it. Actually, you'll see it coming up later on, but before we get there, we have to first prove this identity. So before we prove this identity, let me explain why you should even care about this. First of all, this first summation is a summation over position space, okay? How do you know that? Because it's summing over j's. Remember, x of j is the position of the jth spring in our n-coupled oscillators problem. Now, these two summations over k and q are over momentum space or momenta space, okay? And how do I know that? Because if you look back, then I said that p sub k or p sub q, that is the momenta that's associated with the kth spring or the qth spring. So here we have the momenta associated with the kth and qth spring, but notice this is not just the regular momenta of those springs, right? How do you know that? Because you see these little tildes here that tell you that these momenta are the result of essentially Fourier transforming the position vectors of the kth and qth springs. Okay, that's really what's happening here. And finally, we have this little exponential piece that's essentially coming from e to the ikx, x of j, right? It's essentially a plane wave, but now you see that x of j has been replaced with ja, as we did before, and k has been replaced with k plus q, the summation of both momenta, k and q. So essentially, we're going to see this summation pop up over and over again later on, very soon, in fact. So it helps to kind of reduce it right now, prove this identity before we cross that bridge, okay? So that's the reason why we're going to be taking a look at this. So let's go ahead and evaluate this. The first thing I'm going to do is do the summation over j of this integral. Okay, you might recall, as we just proved, the summation over j of e to the I k minus k prime ja is n times the delta function k comma k prime. So now, if I do the summation over j, what am I going to have left? So I'm going to do the summation over j. Let's see what I have left. Let me use yellow. So that'll be nice and bright. So I'll have 1 over n. My summation over j is gone, and I'm going to be left with a summation over k and a summation over q. I'll be having pk tilde, pq tilde, and now here's the kicker. So this exponential, notice that here I had minus k prime, whereas here I have plus q. So in this case, q takes the role of minus k prime. So that means instead of delta k k prime, I'm going to have delta k comma minus q. Okay, so I'm going to have delta k comma minus q. And don't forget, I have this factor of n popping up over here. So that means I should have these two cancel out. And so I should be left over with a summation over k, a summation over q, pk tilde, pq tilde, delta k comma negative q. Let's check that, and indeed, that is correct. Very good. Now, the next thing I'm going to do is just evaluate the summation with the power of the delta function. The delta function demands that k equals minus q, otherwise the summation dies, right? So if I take a look at this, look what's being summed over. First, I have a summation over k, then I have a summation over q. And I know that this summation only exists if k is equal to negative q. So that means this inner summation over q, is going to do whatever it can to survive. And it can only survive if q is equal to negative k, right? K equals negative q is the same thing as saying q equals negative k. And therefore, this entire thing reduces to a summation. Let me make sure that I'm writing this correctly. Good. So this entire summation reduces to a summation over k of p sub k tilde p sub minus k tilde. Where did minus k come from? Well, this used to be q, but now q is equal to negative q by the power of the delta function, and so my summation has now been reduced to this. So what has used to be a summation over 3 variables is now a summation of only one variable, a summation over the variable k. So that right there is the power of the delta function and the power of the identity that we had proved earlier. So this is going to show up again and again. So it's very important to remember, not remember this fact, but to see where it comes from. Now we're going to employ this fact right now. So let me first write out what we have just proved. We've just shown that 1 over n times a summation over position and momentum space of pk tilde pq tilde e to the I k plus q j a is no more than a summation over k of pk tilde p minus k tilde. Okay, very well. So that is the identity which we have just proved or proven. Okay, so now we're going to employ this identity to evaluate our Hamiltonian in momentum space. Okay, so let's go ahead and do that. So the first thing I'm going to do is remind you what our Hamiltonian for the system is. Let's come over here. Hopefully you'll see what I write here. So the Hamiltonian for our n-coupled oscillators is made out of summation over j. So the kinetic and potential energy associated with each one of these springs. So a summation over the jth spring, where j goes from 0 to n. So now, what is the kinetic energy associated with each of these springs? That's simply going to be 1/2 m. Oh, sorry, am I writing this correctly? Well, you could write 1/2 x sub j dot squared, but typically we express it in terms of momenta as p sub j squared over 2m. Okay, and the potential energy associated with each of these is going to be 1/2 k, and here's where the coupling used to come in, xj plus 1 minus xj squared. Okay, so now we're going to break this down. First, let me just write that whole Hamiltonian down here. So our total Hamiltonian used to be the summation over j of p sub j squared over 2m plus 1/2 k x plus j plus 1 minus x sub j squared. So we're going to take this Hamiltonian, which is a coupled Hamiltonian, because as you can see, the j plus 1th spring has its position coupled to the jth spring by virtue of the spring potential energy. We're going to uncouple this Hamiltonian by expressing it in momentum space. Let's check that out. So now we're ready to transform our Hamiltonian from position space to momentum space. Let's do it. So let me pull up the blackboard. Let's get to work. Okay, so the first thing I'm going to do is rewrite our Hamiltonian from before. So here's our Hamiltonian for our spring system. So the Hamiltonian is the summation over all the springs j from 0 to n, and we're going to have our kinetic energy term, pj squared over 2m, plus our spring potential energy term, 1/2 k j plus 1 minus j squared. Right, so this is our Hamiltonian for our system, for our spring coupled oscillator system. Now, we recall that we had the following transformation from position to momentum space, right? So let me first, maybe I should write it over here on a lower board so that we can just compare between this and another calculation. So let me write it over here. Hopefully you'll be able to see. So first of all, our kinetic energy term is going to be replaced as follows. We had x sub j, okay, that came from transforming x sub k from momentous space by using e to the I k j a. Okay, let me just ensure that I'm writing it correctly without any mistakes. So indeed we have xk tilde e to the I k j a. I forgot a 1 over square root of n normalization factor. And likewise, p sub j is very much similar, summation over k, the wave vectors of p sub k tilde e to the I k j 1 over square root of n. Okay, so very good. This is our x sub j and p sub j. And so now we're going to go back here and plug all of this into our original Hamiltonian, right? So let's go ahead and do that. So first of all, I recall that my p sub j, let me write my p sub j here. P sub j is the summation over my momentous states k of e to the I k j p sub k tilde 1 over square root of n. Let me make sure that I've written it correctly. This is p sub j 1 over square root of n summation over k p sub k tilde e to the I k j a. So let's go ahead and first do the kinetic energy term. We're going to have T is equal to the summation over j of p sub j squared. So this is going to equal, so I'm going to replace p sub j by this summation here. So I'll have the sum over k of e to the I k j a p sub k tilde 1 over square root of n. And since this is squared, I'm going to have two of these terms. So 1 over k and 1 over k prime, let's say. K, of course, is a dummy variable. This is just k prime for my second summation over the momenta states. Okay, so this should be my kinetic energy. Hopefully that is correct. Let me make sure I did not make any silly mistakes. So right now I'm going to simplify this a bit. Let's pull this over here. 1 over square root of n, 1 over square root of n gives me 1 over n. I have now the summation over k and over k prime of e to the I k plus k prime ja of pk, and this should be k prime, pk prime. Okay, and that should be it. Let me just double check. Okay, very good. So I have all of this, and one thing I did forget is this summation over j at the very beginning. So there should be a summation over j all the way out front over here. Okay, so now let me write down my entire kinetic energy without missing any terms. So I have a normalization factor of 1 over n. I have my summation over j, my summation over the momenta states, k and k prime. I have e to the I k plus k prime ja pk tilde pk prime tilde. Now, if you recall, we proved an identity regarding this mathematical statement just a few boards ago. Okay, let me just copy down the results of that calculation. We showed that 1 over n, the summation over j, summation over the momenta states of e to the I k plus q ja p sub k tilde p sub q tilde was equal to the summation over k of p sub k tilde p sub minus k tilde. So that means in this case, we have the exact same kind of summation here, except instead of q, I have k prime, right? So all of this really should reduce to simply the summation over k of, let's see, of the same thing, p sub k tilde p sub minus k tilde. Okay, let me just ensure that I've got the correct results. Let's see. Indeed, that is our new potential, our new kinetic energy term. This is our kinetic energy in terms of momenta states. Okay, so this is our kinetic energy after we have transformed it from position space to momentous space. So in position space, it looked like pj squared. Now in momentous space, it looks like pk tilde and p minus k tilde. Now I'm going to do the same kind of physics with our potential energy term, which was originally the big hassle, right? That was what was being coupled together originally. So now let's take a look at our potential energy term. So recall our total Hamiltonian is made out of our kinetic plus potential energy terms, and our potential energy term looks as follows. It's the summation over all the springs of 1/2 k xj plus 1 minus xj squared. Okay, so now we want to decouple this by going to Fourier space. So recall that we had x sub j is the summation over all the momentous states k of e to the I k j a x k tilde, right? So now I can use this to rewrite this difference over here. Okay, this is the critical part right here. So pay close attention. So this is x sub j, that's fine. And what about x sub j plus 1? Well, that's simply going to be e to the I k j plus 1 times a xk tilde. So now if I go ahead and subtract x sub j from x sub j plus 1, that's going to result in the summation over k of e to the I k j plus 1a minus e to the I k j a times xk tilde. So now if I go ahead and factor out e to the I k j a, that's going to give me e to the I k a minus 1 times xk tilde, right? So I have all of this remaining after I factor this out. So if I do this over here, let me go ahead and pull this up a little bit. This is going to give me what? Let me just write down what we just discovered. We just discovered that xj plus 1 minus xj can be rewritten as a summation over k of e to the I k j a e to the I k a minus 1 times xk tilde, right? So we're in the process of decoupling this potential energy term. And so now let's see what happens if I square this. If I square xj plus 1 minus xj, that's going to repeat the summation. So I'm going to have a summation over k, but also a summation over k prime, okay? So I'm going to have two of these. Okay, so I'm going to have an e to the ikja term, but also an e to the ik prime ja term. And likewise, I'm going to have an xk tilde term, but also an xk prime tilde term, okay? And finally, I'm going to have two of these terms as well. I'm going to have e to the ik minus 1 times e to the ik prime a minus 1. So this is my entire summation here. And so now let's see what's going to happen. First thing I'm going to do is recall what I had proved just previously. Okay, previously we proved that 1 over n times the summation over position and momentum states k and q of e to the I k plus q ja times pk tilde pq tilde is equal to, let me see, what did we prove? This is equal to the summation over k of pk tilde times p minus k tilde. So now if we just go ahead and employ this over here, e to the ikja xk tilde e to the ika minus 1, we can use that to vastly simplify this summation. So let's go ahead and do that, okay? First thing I'm going to do is write this down in this form so we can see how it simplifies down, okay? So we have, first of all, notice that we have our omnipresent summation over j. So we definitely have that term. So we have a summation over j. And then we have a summation over k and k prime here. So summation over k and k prime. Okay, so now we have these two terms. So I have e to the I. Now instead of q, I have k prime here, right? So k plus k prime, ja, okay? So that's what I have so far here. And then I have pk tilde, pq tilde. Instead of that, I'm going to have xk tilde and xk prime tilde, right? So this is going to be xk tilde, xk prime tilde. Okay, so I've written down most of my statements over here, except for these two exponential terms. So all of this reduces down to what? All of this reduces down to the summation over k of, now, instead of p sub k tilde and p sub minus k tilde, I should have x sub k tilde, x sub minus k tilde. Let me just ensure that that is indeed correct. Going back. Indeed, that is correct. Okay, very good. So now that I've simplified this summation, I can use that result to rewrite this entire sum down over here. So let's rewrite that entire sum over here. So the first thing I'm going to do is write what we had over here. Hopefully you can still see. So xj plus 1 minus xj squared was equal to the summation over k. Now, by the way, this was also summed over all j. So I guess I should first write that. Let's first write the summation over j, and then the summation over k, summation over k prime. And then we had e to the I k j a. And in fact, we also factored this out. We combined these terms. So I had e to the I k plus k prime j a. And we have xk tilde, xk tilde, xk prime tilde. And so now if we employ our summation trick from here, then all of this simplifies down to xk tilde, x minus k tilde. Okay, now don't forget we also have our two exponential terms over here, which is, let me write those down as well. We have e to the I k a minus 1 and e to the I k prime a minus 1. So what we've just proven is that all of this part of the summation boils down to the following. This is all equal to the summation over k of xk tilde, x minus k tilde. So that means our summation, our original summation over j of this coupled term, xj plus 1 minus xj squared, becomes the summation over k of xk tilde, x minus k tilde, times, now in the process of doing that, what we did is we said, notice that in the process of simplifying our summation, k prime became negative k. And so here k prime is also going to become negative k. So I'm going to have e to the I k a minus 1 times e to the, now instead of k prime, I'm going to write minus, yikes, minus I k a minus 1. And now I can go ahead and simplify this, right? So let's go ahead and simplify this expression right here. I'm going to, this is just going to be basic algebra from here on. So I'm going to just FOIL this out. E to the I k a times e to the negative I k a minus e to the I k a, okay, minus e to the minus I k a plus 1. Okay, that's just this thing FOILed out. Now, of course, this term right here is manifestly 1. 1 plus 1 is 2. So I'm going to have 2 minus, now here I have e to the I k a minus e to the minus I k a. Now what is that if not 2 cosine k a? So this right here becomes 2 minus 2 cosine k a. Okay, so now all of this boils down to rewriting this maybe as one term. And in fact, we can rewrite this as one term. I'm going to show you how in just a second. So let me factor this out. So I have 2 times 1 minus cosine ka, and maybe I can drop down one of the lower boards to simplify this further. Okay, So now I have 2 times 1 minus cosine Ka. Now it becomes really just a simple math problem to simplify this down further, but we recall that cosine of 2Ka is simply cosine squared Ka minus sine squared Ka, so that cosine of Ka is cosine squared of Ka over 2 minus sine squared of Ka over 2, so that cosine squared of K over 2 is simply 1 minus sine squared of K over 2, which combines with this to give us 1 minus 2 sine squared K over 2 is cosine Ka. So now, if I go ahead and negate both sides, then I'm going to have minus 1 plus this. And now if I just add 1 to both sides to reproduce 1 minus Ka as in here, then I'm left with 1 minus cosine Ka is equal to 2 sine squared Ka over 2, meaning that my entire expression over here, 2 times 1 minus cosine Ka, becomes 4 times sine squared Ka over 2. All of this long song and dance to say, to find the fact that this thing over here, my potential energy term, becomes the summation over K. So my potential energy term, which used to be xj plus 1 minus xj squared, this coupled term now reduces to the summation over K of, where did I write it down? Xk tilde, x minus k tilde. So I have xk tilde, x minus k tilde. And then all of this term, remember, all of these exponentials boil down to 2 times 1 minus cosine Ka, which we just showed is the same thing as 4 sine squared Ka over 2. So this becomes 4 sine squared Ka over 2. So this right here helps us decouple our Hamiltonian. And so now we can write our full Hamiltonian, right? Our full Hamiltonian, recall, was the summation over all the springs J of Pj squared over 2m plus 1/2 k xj plus 1 minus xj squared. Right? Now we can go ahead and write all of this as follows. Our Hamiltonian is now, let's see, so I have the summation. Now, first of all, I have my 1 over 2m term. Now, pj squared, if I look back, what did that become? That became a summation over k of pk tilde and p minus k tilde. Let me make sure that's correct. Indeed, it is. So that is my kinetic energy term. And now plus my potential energy term, which is xk tilde, x minus k tilde, times this sinusoidal, 4 sine squared Ka over 2. And this, ladies and gentlemen, is my decoupled Hamiltonian for n-coupled oscillators in momentous space. So this is the Hamiltonian for my n-coupled oscillators in momentum space, which is xk tilde and pk tilde. So this is our final achievement. This shows that we can decouple n-coupled oscillators by transforming from position space to momentous space. So that concludes our lecture for today. We'll see you in the next one.